we now want to give an introduction to Kepler's laws and talk a little bit about how Kepler came up with the laws and what they meant for Isaac Newton as he was developing his theory of gravity. Okay, so Johann Kepler was an astronomer, and he was born in 1571 and died in 1630, and he was German. Right now, he was a fairly brilliant mathematician, and he lived during the same time period as Galileo did. Galileo lived a little bit longer, dying in 1642, but the two never met. Now, they did correspond. Okay, Kepler and Galileo did have some correspondence. And Kepler actually wanted to look through a telescope, but never actually got his hands on one. But in any case, as a young man, Kepler entered the service of the royal astronomer of the Dutch kingdom. His name was Tycho Brahe. And after Tycho's death, Kepler inherited all of Tycho's data. Now, you need to know something about Tycho. And that is, being the royal astronomer in the Dutch kingdom, he had access to the best, at the time, observatory in the world with the best instruments. He had world-class instruments. Now, the telescope had not been invented yet. When Kepler was a young man and started working for Tycho, the telescope was on the horizon. It had not yet been invented. But Tycho did have the most precise instruments of the day. And his job, or at least part of his job, was to go outside at night and take very, very careful measurements, not only of the stars, but also of the planets. So with instruments like sextants and compasses, he would measure very, very precisely angles, right? How many angles in degrees above the horizon a particular object was, and how many degrees it was from any of the cardinal points. Okay, and he had the best instruments in the world at doing so. So he cataloged for years the highest quality astronomical data the world had ever seen. Okay, now, so that was Tycho. That's what he was about. And Kepler inherited this data. Now, Kepler was actually hired by Tycho to solve the planetary orbit problem. And why were planetary orbits a problem in the first place? Okay, well, in the oldest system, well, not the oldest system, but in the old system, the accepted system at the time, right, at the beginning of the Renaissance, people still ascribed, by and large, to the Ptolemaic system. And Ptolemy was an ancient Grecian astronomer, and he did not necessarily develop the basis for this system, but it does bear his name, as he did a lot of work on it, and actually produced the tables, astronomical tables of observations, and predictions using this method. Okay. And this is called the epicycle method. So in the old system, the geocentric system, okay, I really should put geocentric here, and geocentrism, okay, geocentric, all right, so geocentric, okay, means Earth-centered. Okay, so it means Earth-centered. So in the old system, the Earth, which would be right here, okay, is the center of the universe, essentially, and everything orbits around the Earth. Now, in the geocentric system, okay, in the geocentric system, you have a few different things. Number one, the length of the arm that a planet spent away from the planet was called the equant. Okay? Or I'm sorry, the deferent. And the deferent also you can think of as the essential essentially the average distance, if you will, the average distance along the circumference of this circle that a planet would spend away from the Earth. Okay. Now, one thing to note, ancient Greeks highly prized the shape of the circle, right? They highly prized the shape of the circle. And so their initial thought process, their thinking, was that all orbits had to be circles. Now, they knew that the Earth was not at the center of most of the circles of the objects that they were observing. That just didn't fit the observations. But they still thought that the orbits themselves were perfect circles, even if the Earth was not at the center of that circle. So that's why you might, pardon me, you might see the Earth kind of offset just a little bit, right? So in this diagram, this dash, okay, would represent, that dash right there, would represent the center of the circle, and the Earth is offset somewhat, okay? So the Earth being offset accounts for the fact that the observations just would not allow the placement of the Earth at the center of the circle, but the circle itself was still a perfect circle. Now, there were some problems with planetary orbits, and namely, the planet, as it's moving through the sky, would usually seem to go backwards from time to time, right? So planets typically follow the directions of the stars, but from time to time, they move backwards. And this was a real problem for ancient astronomers to explain. And so the original idea to explain this was to introduce what's known as the epicycle. Okay? So the epicycle. Now the epicycle is this circle here that orbits all along the deferent. Okay? And so what happens is this planet is orbiting along the epicycle, while the epicycle is orbiting along the deferent. Okay? And what this produces is a fairly complex system of motion. Right? So that was how they explained the planets to seem to move backwards from time to time. Right? Most of the time they would move in a preferred direction, and then when the planet was at the bottom of the circle of the epicycle, it would reverse direction and move backwards against the sky. And that was the earliest explanation for this, what we call retrograde motion. Okay, so retrograde motion is nothing other than when a planet is moving against the general preferred direction of stars. Okay, so that's the old system. That's the Ptolemaic system. And that was the system that was in place when Kepler started working with Tycho's data. Now, Kepler was not convinced that this system was correct. He was actually a heliocentricist. He believed the sun was the center of the solar system, but he couldn't prove it mathematically. He didn't have the observations to actually work out the mathematics of being able to place the sun at the center of the solar system. And that was one of the reasons he actually took the job with Tycho, was specifically to prove that hypothesis. So, what happened is, and I maybe should come back to this slide, after Tycho's death, okay, after Tycho's death, he was able to actually crack this puzzle. Now, it took him a lot longer than he originally intended, okay? He originally thought he would be able to solve the problem in just a few months, and it took him several years, right? 8 years, if I'm not mistaken, to work out the orbit of Mars. And Mars, there are reasons why Mars was the orbit that was one of the most befuddling, if you will, for the ancient astronomers. Mars caused the ancient astronomers more headaches than any of the other planets. And so that was the planet that Kepler really wanted to focus on. Now, so what did Kepler discover as a result of working with Tycho's data on the planets and their positions? So what he realized is if you hold to a heliocentric position, if you hold to a sun-centered model, the closed orbits, or orbits that complete their cycles, objects aren't flung back out after passing close to the sun, for example. As long as the orbit is closed and stable, then the shape is going to generally be an ellipse. And this was also surprising because it flew in the face of the fact that the Greeks argued that it should be a perfect circle. And as a result of this, Kepler discovered 3 laws. And the first law is that all orbits are ellipses and the sun is at one focus. Now, don't worry too much, okay? We're going to explain what ellipses are shortly, but keep this statement in your back pocket for the moment, okay? And number 2, all orbits are going to sweep out equal areas in equal times. And number 3, the square of the orbital period is equal to the cube of the semi-major axis, okay? Now, there's a lot in that statement, okay? But we're going to unpack it, so don't worry. But let's come back up here to this ellipse idea first and reiterate that this was absolutely a breakthrough because it absolutely broke with the tradition of perfect circles, right? The ancient Greeks absolutely believed that orbits were perfect circles. And even when Copernicus wrote his work, the essentially first codified version of the heliocentric model, he couldn't get away from perfect circles either. He was still a firm believer that perfect circles were the preferred shape, of orbits. And so this idea that ellipses are actually used and are the shape of orbits was quite extraordinary. Okay, this was quite an extraordinary leap, and I cannot stress just how much. So in the next video, we'll talk about what these 3 laws are, but for the moment, with the time we have left, let me at least just explain what an ellipse is, okay? So an ellipse, you can think of it as more or less like an oval, okay? But an ellipse has 2 points, and those 2 points we call the foci, right? The foci. And that's plural for focus, okay? So each of these points is known as a focus, okay? Each of those points is known as a focus. And what's unique about an ellipse, what separates an ellipse from a regular oval, okay, is if I pick any spot on the ellipse, okay? Now my artwork's not fantastic here, but if I pick any spot on any ellipse, okay, then what I find is that the distance from both foci combined is a constant, okay? So if I add up this leg and this leg, I'm going to get a number. And if I add up this leg and this leg, I'm going to get the same number. And it doesn't matter where I am on the ellipse, that will hold true. So the definition, if you want to think of it that way, that is a working definition of an ellipse. And a shape where from the foci, the distance from the foci to the boundary is a constant when I take both foci into account, right? So that's the definition of an ellipse. Now, an ellipse also has some geometry associated with it, okay? So the longest axis that should go through the foci, okay, the longest axis is called the major axis. So from one edge of the ellipse to the other edge of the ellipse, okay, this is known as the major axis. And from the center of the ellipse, right, my circles aren't, fantastic, but from the center of the ellipse out to one edge, okay, right there, that's what's known as the semi-major axis. Okay, semi-major axis, and that is a J, not a G. All right, semi-major axis. And the axis cutting the shortest distance across is called the minor axis, and of course half of that would then be the semi-minor axis. Now we denote the semi-major axis with the letter A, right, and that's going to be important here shortly. But that's the general idea of an ellipse. Now one thing to note also is that a circle is an ellipse with